Okay, hello everybody. My name is Jenny Vázquez. I am PhD student in artificial intelligence. And today I'm going to present my research proposal. Here is you can see my email. And if you ask something, please write me and I answer you as possible. Okay. For today, my presentation consists of the following. I will tell you in general terms about my research and theoretical framework that supports all of the work I'm doing, and emphasizing the problem that I motivate us to carry out this work. I'll present you the proposed algorithm, the methodology under which the experiments have been carried out. I'll present you some results and the conclusion and future work. Okay. In 1995, Judaper presented us a method to obtain causal estimation. And this method works from a conventional Bayesian network. And in previous work, we tested this operator of intervention of variables and detected its efficacy and causal estimation. However, he also found some opportunities for improvement. For example, traditional algorithms to build Bayesian networks don't include validation of causal relationships. That is, sometimes the direction of the arrow into the network doesn't allow us to realize an intervention of variables. This was our principal motivation. And starting from this proposed, we proposed two algorithms that include causal learning for building Bayesian networks. These algorithms belongs to the cognitive psychology, and the results they have produced so far interesting. Okay, so we know that a network is directly a cyclic graph in which the connection between the nodes represent conditional dependence between the variables. These models are used for obtaining probabilities estimates and belief updates, but their results are not used to make causal interpretation. That is not recommended. So from the models, we can obtain the probability expression, which will allow us to make questions into the network. So, for example, the probability expression, in this example, the probability expression looks like this example for this simple Bayesian network. But in the causal Bayesian network is another possible name for that, is also a cyclic graph, similar to a conventional Bayesian network. However, in these models, the connection between the nodes should represent causal effect relationships, allowing for the intervention of variables, from which will be obtained new probabilities, and these new probabilities could be causal probabilities. So, in this example, you can see when they connect the intervention of variables into the node B. It's a simple example. Okay, according to Peirce, each intervention requires surgery on the network, in which the parents of the causal variable are removed, and through a set of inference rules, a causal path between the causal variables and the effect we can obtain. Once we have the causal rule, it's possible to get a new expression of probability. But this new expression is similar to, in my example, it's a simple example, like this, when we are removed all the arrows from the variable, the possible causal. So this expression will allow us to calculate the new probabilities. The new probabilities allow us to see the difference between the observation and the intervention is according to Peirce 2. And the observation is exclusive of the queries to a network without intervention. Okay. From the new probabilities, it's possible to obtain the causal effects or the average causal effect. What basically tells us if a variable can be the cause of another when one value of the cause is present and another is absent. So the equation is like this. Okay. So as I mentioned earlier, the result obtained from the intervention of batteries and the test on the U operator gave good results, allowing us to appreciate the difference between observation and intervention. However, the network originally obtained through traditional algorithms don't contain causal learning, provoking that some of the intervention couldn't to be done. Okay, sorry. The problem in our first work, we reported that only 10% of the interventions performed found causal root. That's provoked that the Bayesian network obtained through traditional algorithms be modified or even something even drawn manually by the experts who provide us with the data. Okay. Or propose, is integrate causal learning into two Bayesian network algorithms. And the first correspond to the Rescorla-Barnett model, and the second one to the PowerPC theory, both coming from the cognitive psychology. And we decide to use this algorithm or this proposed because they have been widely tested in the area of the study and given results very similar to natural causal learning. Okay, so very fast, algorithm consists of looking for the conditional dependence of the variables in each data set. Once it has been determined that each variable can be connected with another because for its conditional force, we use the Rescorla-Barnett or PowerPC model, depending with the algorithm we are running. And with this, if these both variables can remain connected. If the learning results between both variables is major to the threshold that we propose, an arc between the two variables is placed to direction. In the first proofs, we only put an arrow and connection with that arrow with direction. And then if the proof with the model of psychology, cognitive psychology, pass this threshold, we put an arrow with direction between the two nodes. If the causal learning result between the variables indicate that they are not causal, the connection is eliminated. Okay, so each dataset was carefully selected because it's necessary to be sure that they are at least two variables that have a causal relationships in them. The data pre-processing is not included in the proposed algorithm, so it must be performed separately. And to carry out this process, we make use of the discretized and Cain algorithm these are in the software way. And the algorithms for the creation of the new network, we are named according to the method of cognitive psychology. So for the first method correspond to the Rescorla-Barnett method, we call them bien RW. And for the second method is the PowerPC theory. We name CVM PWPC. Okay, so for the construction of the Bayesian networks, we create two networks for each algorithm. And once we have the network, we select the variable, the possible variable is the variable for to intervenate. And we indicate a value for this variable. As well, we indicate the effect variable. And then we search the causal path or the causal root. In the program, we use the causal effect library in R. So in the program R, if there is a causal root, the system extracts or delivers the new probability equation, which show the causal probabilities must be calculated. An example is like this equation. And once I obtain the new expression, it's possible to calculate the causal probabilities tables. The expression is broken and separating to the conditional probabilities and sum about which the calculation will run. And then it is possible obtain the tables of probabilities tables. And sometimes we need to make a normalization on these tables. And then once the probabilities table are obtained, we can calculate the causal effects. Okay, so I present you a few results that we obtain. For example, this is a data set. This Bayesian network corresponds to a data set of breast cancer. This is with the algorithm with PowerPC theory. And the the left, we can see the Bayesian network obtained with or proposed. And the right, the intervened Bayesian network. The nodes in color blue represent the causal path in the intervened Bayesian network. And the nodes in the color blue too in the Bayesian network only represent the possible cause and the effect. So after we obtain this Bayesian network and after we make an intervention of variables, we can obtain the probabilities. In this example, you can see the difference of the probabilities after intervention and after the intervention and the differences between the observation and intervention. And you can see the causal effect for two possible values on the same causa. And then we are on another, this is another results is for the same data set, but in this case is with the other algorithm, is for the Rescorla-Barnett model. And you can see the Bayesian network in the left, and the right, the intervened Bayesian network. The same, all of the nodes in color blue represent the causal path. And then we obtain the new probabilities, and you can see the differences between the observation and intervention. They are different. And we obtain a causal effect for this variable. It's the same effect, and we take two values for the possible causa, and then we can use the result for make some interpretation that they can use the result in causal terms because it's possible in this part of the interpretation. So we have another dataset. It's the same, the Bayesian network with PowerPC method. Theory per network is in the right. And then we obtain the new probabilities. And the same, we can see the differences between the probabilities of the observation or intervention. And the causal effect is obtained too for this example. And then the same result with the same data set, we obtain the two networks after the intervention. And you can see, in this case, every nodes are in blue because the rules of the intervention select all the nodes. So this is the probabilities for this example. Again, we can see the difference between observation and intervention of variables. And this is another example for Lucas. This is only the Bayesian network with the PowerPC method, PowerPC theory, and Roscoe-Lavanet. This is the result and this is some results of the probabilities. Okay, I only show you some results because we are in process to make more analysis, and we have some real data sets, but we don't have permission for show in this presentation because we are in process to analysis, but I hope soon we can show these results. So our proposal consists of, our proposal is, we have good results. The intervention through the operator provide us good results, and we can see the differences between the intervention and observation. We can corroborate the efficiencies of this operator. And now we can include these two methods of cognitive psychology, and we have increased around 30% the numbers of causal groups obtained with the new algorithms. But we need to work a lot because it's necessary to continue the test with the real data. It's necessary to make tests with different learning rates because we have noticed that when we change the learning rate in the cognitive psychology methods during the algorithm is running, allow us to eliminate more arcs during the construction of the networks. So it is important for us because sometimes our Bayesian networks are many connecting, and sometimes we need to eliminate some connection. We need to consider the hidden causes. Is also a future proposal to improve our algorithm. Okay, some references, a little references. And okay, it's all. Thank you for your attention.